We'll go ahead and do that. Last time we were talking about how perfect everything has to be in order for a baby to be developed. And it does. Everything has to be perfect. There has to be a proper number of chromosomes in the sperm and in the ova. And if that doesn't take place, of course, then impregnation is not going to take place. As I said last time, one of the problems we're having now is, potential problems in the future, is that sperm counts are going down, and we're not exactly sure why. We don't have any clue as to what's going on. They're just getting lower and lower and lower. It could have to do with pollution. It could have to do with some of the substances that people are consuming, marijuana specifically. Alcohol, of course, lowers your sperm count. Alcohol also increases your estrogen level, which is kind of exciting. If you're a female, it doesn't make any difference. If you're a male, it means that you're not going to be quite as masculine as you were before. As odd as that seems. Anyway, everything has to be perfect in order to make a baby. The miracle is that there are so many babies out there, and almost all of them are perfect. Working in a nursery, in a neonatal intensive care unit, and in a nursery in hospitals, I can tell you that very few babies are born that aren't perfect. Almost every baby is perfect. Jimmy Kimmel's, if you know who Jimmy Kimmel is, Jimmy Kimmel's son was born with a heart abnormality. That is so extremely rare. I mean, it almost never happens. Just about every baby is the most perfect structure that you can possibly imagine. It's really quite amazing. So if pregnancy takes place, then probably the offspring will be perfect. For implantation to take place, the uterine wall must be ready for implantation. The zygote must implant at the top of the uterus. If it implants, the lower it implants, the more likely that the baby will spontaneously abort at some point because of weight. There's a lot more there's more support. The higher in the uterus, the more support there is. Let's see. Boy babies tend to implant high, and girl babies tend to implant low. But girl babies are lighter or smaller than boy babies. The zygote must implant near the top of the uterus. I've already said that. Adequate vascularization must take place between the embryo and the uterus. Fibroid uterus, for example, has a problem with vascularization, and because of that, it's very difficult for a woman who has a fibroid uterus to make a baby, to carry a baby full term. Growth and cell division must take place on a continual and a balanced pattern, and of course this is the problem with individuals who are drinking, who smoke cigarettes, and individuals who drink alcoholic beverages, or take any other drug. I mean, all the drugs really mess up the balance and the continuation of the cell division. It's really kind of interesting. Cigarettes, of course, are vasoconstrictors. So as you are smoking, if you're smoking during pregnancy, what you're doing is you're starving the child for blood. You're starving the child for nutrients. Alcohol, the worst pattern, and we've discovered this looking at babies that were born to alcoholic mothers. What we've determined is that a woman that drinks a lot all the time doesn't have nearly as much damage as a woman who drinks a lot, who binge drinks. I know. Normally, if you drink a lot of alcohol, and of course, if you drink all the time, then you don't drink as much as if you binge, because when you binge, you drink to the point of not just inebriation, but a lot of times to passing out. And for that reason, of course, during that whole period while she is snockered, the baby isn't getting proper nutrition. So it's kind of everything's fine, and then there's no growth taking place, and then everything's fine, then no growth is taking place. And that's one of the reasons why FAS is such a destructive problem. As soon as the sperm penetrates the ova, the structure becomes a zygote. So it starts out as an ova and sperm, and once they get together, it becomes a zygote. It's going to stay a zygote for about 2 weeks. It's going to stay a zygote until it implants on the uterine wall. So the zygote is the structure that's migrating down the fallopian tube and implanting on the uterus. So for the first 2 weeks of pregnancy, the mother doesn't know. There's no feeling. Nothing has really changed. The only thing that's happening is that she has this alien structure floating around down her fallopian tubes and into her uterus. And it's floating around and trying to find the best place to implant itself. This takes about 2 weeks. Within 12 hours after the ova has been impregnated, it starts dividing.
Is this how they determine pregnancies or pregnancy tests?
Pregnancy tests. Okay. What happens is the zygote starts producing a substance called human chorionic gonadotropin, which we call HCG. So if you ever see HCG, it's small h, capital C, capital G. HCG, it produces the HCG to protect itself from the mother's immune system. Because as far as the mother's concerned, this is a cancer, it's an alien structure, it ain't part of her. It's half of her, but it's only part of her. So it produces HCG in order to protect itself. So what happens is the more cells you have, and remember after 12 hours, now we have 2 cells, and then fairly quickly we have 4 cells, and then fairly quickly we have 16 cells. The more cells you have, the more human chorionic gonadotropin. Each cell protects itself with this chemical substance, telling the mother's immune system to leave me alone. That's what it's doing. So it produces HCG. So the more cells you have, the more likely, the more HCG you have, the more likely that you're going to be able to detect that the mother's pregnant. Does all that make sense?
Yeah.
So the Clear Blue Easy is just detecting HCG. This will all be expelled in the urine, and for that reason you can usually tell if somebody's pregnant with a urine specimen. And we're getting more and more sensitive tests all the time, as it were. Once upon a time, it was very difficult. It took about a month before you produced enough HCG, or the fetus was producing enough HCG to detect. Now here's the kicker. So HCG tells the immune system to leave it alone, to leave the structure alone. Of course, without HCG, there wouldn't be any babies. Without any babies, the species would have died off a long time ago. However, when somebody gets cancer, let's say you've got a tumor, you've got a cancerous growth on your lung. As long as it stays in the lung, then the immune system will encapsulate it. It will capture it, and it will cover it with a mucoid structure. It will keep it from growing. That's what the immune system will do. However, if the cancer metastasizes, if it develops the ability to move from one place to another, then what will happen, it'll start sending off cells, and those cells will implant someplace and they will become cancers. The reason that it's able to do that without the immune system killing it is because the cancer will start producing HCG. And once it starts doing that, your immune system has no clue that you've got a problem, that you've got a cancer. Okay, so HCG, as far as babies are concerned, we wouldn't be here if it wasn't for HCG. However, so many people die of cancer, but usually they don't die from the first tumor. They usually die from the second, the third, the fourth, the fifth, as odd as that is. So HCG actually protects the cancerous structure. Normally, if we can catch it early enough, if we can catch the cancer early enough, then we can knock it out before it metastasizes. Once it metastasizes, it becomes far more difficult to treat. Tom Petty died yesterday. I don't know if you heard that. I didn't hear what he died from. I guess he collapsed at his home and he was DOA when they got him to the hospital. I don't know. You didn't hear why he died. Probably a heart attack. He's only 66, pretty young fellow. He said, being 68 years old. Anyway, okay. So we've got a zygote that is implanting itself on the uterine wall. When it implants itself on the uterine wall, it will tie into the mother's circulatory system, and it will start feeding itself from the mother's blood. So at this stage, anything the mother does, the baby does. So if she gets drunk, the baby gets drunk. Well, not really, because it's not that kind of a structure at this point. But if she uses alcohol, then the alcohol can get into the baby. A lot of times, most things will not cross the placental barrier. As it turns out, most chemicals won't cross the placental barrier. And for that reason, a lot of things that she does will not affect the baby. There are only select things that will affect the baby. Within the 2 weeks, the zygote becomes an embryo and divides into 3 distinct layers. The 3 distinct layers will become the skeletal system, the nervous system, and the digestive system. Nervous system develops from the outer layer of the 3 layers, the ectoderm, and ectoderm just means outer layer, outer skin. The ectoderm grows into a flat oval plate. The cells of the plate do not grow at the same rate, and a groove develops in the middle of this plate. As you can see, that's what's taking place here. It's developing the groove develops, and then it closes off, and it becomes a neural tube. When it's still the groove, it's referred to as the primitive streak. Okay, so how old is the baby? 3 weeks old, 4 weeks old. And we still don't have, we have the beginning of a nervous system, but we don't have a nervous system yet. As the cells continue to divide, the groove slowly grows into a neural tube. The front or anterior portion of the tube divides into 3 structures that will become the hindbrain, the midbrain, and the forebrain. So the brain isn't developed yet, but it is developing in a way. In a way, it's developing. It just isn't a structure yet. There's the baby at the 8th week. By this time, it's developed all of its rudimentary organs. The brain at this time takes up about half of the fetus's mass. As you can see, it's about half of the mass is the brain. Brain will continue to go through the teenage years. Actually, it will grow until you're in your mid-20s. Nervous system development takes place in 6 stages. Neurogenesis, the formation of neurons, cell migration, movement of neurons from nerve cells, cell populations. Differentiation takes place, development of distinctive types of neurons. Synaptogenesis, development of synaptic connections as axons and dendrites grow. The neuronal cell death, selective death of neurons and synapse rearrangement. Refinement of synaptic connections. And all of those things are the 6 stages of the neural growth. The first stage of nerve system development is neurogenesis. This is when the nerve cells are produced. Nerve cells themselves do not divide, but pre-nerve cells, which are located in the inner layer of the neural tube, do divide, and they create a closely packed layer of cells called the ventricular zone. And this is a ventricular zone here. Oddly enough, glial cells and nerve cells look exactly alike, and they come from exactly the same place. Scientists are not sure exactly why glial cells become glial cells and nerve cells become nerve cells, because they have the same source. So they're not exactly sure what makes a glial cell and what makes a nerve cell. The cells of the ventricular zone continue to divide and give rise to daughter cells, which also divide. All the body's neurons and glial cells are derived from ventricular mitosis. Neural cells will be completely developed by birth. Each neural structure in the brain will develop at the same time in gestation for all humans. So and this is one of the things that we are very much aware of. All babies grow in about 9 months. Yeah, I know. 28 weeks. In about 28 weeks. Really kind of odd. And the same process takes place with all babies. Now you would think, if we look at if we look at primates, if we look at great apes, they have their gestation is more variable than humans are. We're all like identical twins, as it turns out. We're all just about the same. Everybody develops at exactly the same rate. The only difference is some babies are bigger than others. Some populations have larger babies than others. But as far as neuronal growth is concerned, as far as any growth is concerned, everything takes place at the same time. So whether you're in New Guinea or whether it's somebody in the United States, it really doesn't make any difference. As far as growth is concerned, all growth takes place at exactly the same time. That's how close we are as far as our genes are concerned. Remember, as far as your DNA and my DNA is concerned, it's 99.5% exactly the same. So the surprising thing is that we don't look more alike. Most of the differences between the way we look has more to do with very minor aspects of ourselves. It's really kind of interesting if we look at, I've got 2 dogs. One of them is a yellow lab and the other one is something else. I'm not exactly sure what it is. They don't look anything alike, but they're both canines and they're both domesticated dogs. But humans our variability isn't that great. If you talk to Sarah's got a little bitty tiny Chihuahua something mix. It's a little bitty dog. And she's also got big dogs that weigh 65, 70 pounds. The variability between those 2 canines is extremely great. But as humans, we're almost the same. The variability is very minor as far as humans are concerned. Neurons of the developing nervous system are always on the move. During the cell migration stage, the cells of the ventricular layer begin to move where they will end up. In humans and other primates, by birth, all the neuronal cells will have found their way to where they always will be. Some neurons will creep down glial cells, known as radial glial cells, and they will migrate to where they are supposed to end up. Neurons can either move down the glial cells or jump from one to the next. They actually jump. This migration is guided by various chemicals called cell adhesion molecules. The cerebrum is formed by wave after wave of neurons till the entire cerebral cortex is formed. As I said before, the cerebral cortex is made up of 6 layers. So the first layer develops first, and then the second layer, then the third layer, the fourth layer, the fifth layer, and then the 6th layer. So it is like, it's like putting icing on a cake, I guess. You put the first layer on, and then you put some more icing on, and then you put some more, depending on how much you're going to put on. I guess you put on different colors of icing. That would make a really big mess. Anyway, that's the way that the cerebrum is formed. Once the pre-neuronal cells reach their destination, genes in the cells begin to make the proteins that are required by neurons. At this point, the neurons begin differentiating into a distinctive neurons of the region that they are in. Okay, so how in the world do they know where they go? What if they go to the wrong place? What if a neuron is meant for your optic region and it ends up in your region of sight, or of, well, that's what the optic region is, of hearing or smell? I mean, what if it ends up in the wrong place? What happens next? Well, that's not the way it works. If a cell makes it to a select area, it starts taking on the job of the cells around it, its neighboring cells. Most neuronal cells differentiate through reduction. They take on the task of their neighboring cells. So no matter where they are, they become whatever everything else in the area does. Some cells are undifferentiated cells and will differentiate into any cell that they are close to. These are known as stem cells. And of course, we have tried to use stem cells. We've attempted stem cell research in the past. Unfortunately, there's a law against doing stem cell research in the United States. There isn't a law against stem cell research anyplace else. You have that look on your face like this isn't right. We should do this. It became a hot political issue. It actually went through Congress that stem cell research would be allowed in the United States. And it was vetoed by the president. It was President George W. Bush that vetoed the bill. Since then, nobody has tried to pass a bill again. Since the president has vetoed it, the Congress has become more and more conservative. It was conservatives that said, well, that's God's job. So evidently it's God's job. No, scientists don't count, and we can't do any more research. Anyway, that's the way it works. Sorry about that. We thought that we might be able to use stem cells to combat all kinds of interesting diseases, Huntington's disease and Parkinson's disease, especially Parkinson's disease. Normally, if somebody develops Parkinson's disease, they degenerate relatively quickly. Michael J. Fox, of course, if you ever watch him on television, Michael J. Fox, his decline has been less extreme. And one of the reasons his decline has been less extreme is because he's Canadian, he's not American. So he can go to Canada and have stem cells implanted in his brain. And that's what's been happening. He's been able to go up to Canada and get stem cells. Of course, anybody could go up to Canada, and of course they'd have to pay for it. But since he's Canadian, they have free medical care, so he doesn't have to pay for it. As confusing as all that is. Anyway, stem cells will differentiate into whatever cell they're around. And for that reason, of course, it has to be your stem cell. We can't use, well, no, it doesn't have to be your stem cell, actually. So I don't know what's going to happen in the future. Other countries aren't doing as much research as we would do in the United States. We tend to give grants to scientists so that they can do these things. But of course, the Canadians are making great leaps in stem cell research, and as Americans, we're not making any progress whatsoever. When neurons migrate to their final destination, they start the process of synaptic genesis, of course. Axons and dendrites begin to web out and make contact with the cells that they are going to respond to be responding to. This is done through swollen ends of dendrites and axons called growth cones. The growth cone reach out using fine filaments. The fine filaments are referred to as filopodia. Sometimes it's a solid plate. And of course, the Latin term for that is lamellipodia, or plates of dendrites, of growth cones moving out. Growth cones are drawn by chemical signals called chemoattractants. Growth cones can also be repelled by chemical signals called chemorepellents. As adults, we maintain synaptic genesis structures, dendritic growth cones, axonic chemoattractants, and chemorepellents. Synapses can be can form rapidly on dendrites and dendritic spines, of course. Number of spines increase rapidly after birth and are affected by experience. So the more experience you have, the more of these cones that you have. So if you have somebody that plays a lot of basketball, then they're going to maintain these growth cones in that area that will allow them to practice basketball and play a lot of basketball. So it all depends on what experiences you have and what you want to do as to what portion of your brain will maintain these growth cones. So if you maintain a curiosity about everything, dealing with everything, and try to experience a lot of different things, of course you're going to maintain growth cones in a lot of different areas. And this will last for the rest of your life. These growth cone areas will be there constantly. And the only reason that they would ever go away would be if you stop doing whatever it is that you're doing. So if you experience a lot of different things and try a lot of different things, then potentially you will maintain a brain that is continuing to grow throughout your life. How long? When do these things slow down and stop? They slow down and stop when you die. So all you have to do is maintain curiosity, and try to experience a lot of different things. And this is one of the reasons why in select countries like the Scandinavian countries, lifelong learning is extremely important as far as they're concerned. And this is one of the reasons why when people retire and stop doing things, their lives change. A lot of times they'll just kind of sit down and croak. Can I say croak? Okay. That's the sound that dogs make when they are in the swamp, calling each other, come here, I'm a frog. Anyway, okay. Okay, so we not only have growth, but we also have death. And it's important to kill off the portion of your brain that you're not using anymore. At select times during our lives, we will prune out the cells that aren't necessary. But we have a constant process of getting rid of cells that are no longer needed or are no longer functional. And this process is known as apoptosis. It's neuronal cell death. It's crucial to brain development, of course, especially during the embryonic stage. You need to get rid of this stuff you don't need anymore. Otherwise, you've got a lot of cells that aren't doing anything. So you just don't need them. You just get rid of them, and that's the way it works. Neuronal cell death ranges from 20 to 80%, varying from region to region of the brain and spinal cord. Efficiency is what we're looking for. The more efficient that our nerves are, our neurons are, the more likely that we're going to be a fairly efficient adult structure. And an area needs only so many neurons and synapses, of course, and as the area grows, more neurons than are needed will flood into the area to ensure that the most perfect neuronal structure and synapse are created. So we have all these extra neurons that are flooding in. So what do we do with all these extra neurons? Well, if we don't need them, if it's not a perfect connection, if we've already got the perfect connection, what are we going to do with the extra ones? We get rid of them. What if everybody goes out for the football team? What are we going to do with 3,000 football players? You only need 100 or so to create a football team. What are you going to do with all the extra people? You get rid of them, of course. You don't need them out there. There's too many people to even try to play a game. They're all standing around doing nothing. So you need to get rid of the extra ones so that you can create a football team. The cells that die are self-selecting to die. They are committing suicide. And of course, a lot of times, so we've got 3,000 kids going out for football, for freshman football. What happens to all 3,000 kids? Well, most of them will quit before the first week is over with. They don't like running. They don't want to sweat. The uniform doesn't fit right. They don't like the pads. The helmet doesn't fit. So they just quit. They just go away. And they self-select. They decide that they don't really want to be a football player. And of course, the coach is paying attention to the people that look like they're going to be good football players. And they are ignoring, which however many coaches you have, they are ignoring the kids that aren't really functional or don't seem like they would make good football players. Football is a game for large people. So if you're 5'2" and weigh 110 pounds, then probably they're going to have a difficult time figuring out what you should do. So you will self-select and you will just quit the team. And that's what these neurons do. They self-select and they quit the team. Of course, in the case of football, you're not going to commit suicide just because you didn't make the team. But in the case of neurons, of course, you will commit suicide. You will go away. And the way that you go away is known as apoptosis. All cells carry a death gene that causes a sudden influx of the release of calcium ions that causes the mitochondria to release a protein called Diablo. Does anybody habla español? Does anybody know what Diablo means? It means devil. It's the devil gene. So it's a protein called the devil. Diablo binds in inhibitors of apoptosis proteins, IAPs, that have been inhibiting a family of proteins called caspases. It's really kind of a fascinating process. It starts out as a cell, then all of a sudden it releases this Diablo. The Diablo releases the caspases, and the caspases break up the protein. Well, once it breaks up the protein, the cell goes away because the cells are made up of protein. So it's really a fascinating process. I had a better film, but they took it off of YouTube. So this is the film that I found. This is from Scotland, so you're not going to understand a word she says. She speaks in a really heavy Scottish accent. There we go. Yeah, see, it's from the University of Dundee. Do you have any noise? You should have noise. Okay. We need noise. Well, you won't have to worry about her accent because we can't even hear it at all. So somebody's turned off the noise.
That sound thing by the computer icon right there.
Right there, right here?
To the right. Again.
Right
there.
Huh.
Then.
Yeah, you got it.
Yeah, move it up.
Via two distinct pathways, called the extrinsic and intrinsic pathways. The first pathway is referred to as the extrinsic.
Here, we'll go back to the beginning. Here we go.
Apoptosis is an important cellular process that allows cells to die in a programmed fashion. Apoptosis plays an essential role in growth and development, such as in the womb, where the fetal hand stretches out of the web, and fingers are formed to the programmed death of the cells in web spaces. Apoptosis also plays an important role in removing faulty cells. For example, pathological apoptosis may induce if cellular DNA is damaged beyond repair. In apoptosis, the cell is broken down from within by proteins called caspases. For apoptosis to occur, these caspases first need to be activated. Cascade activation can happen via two distinct pathways, called the extrinsic and intrinsic pathways. The first pathway is referred to as the extrinsic pathway, because the initial signal comes from outside the cell. This pathway is often initiated by other cells, commonly by subsets of T-lymphocytes. These lymphocytes have a surface molecule known as Fas ligand, or Fas-L for short. The extrinsic pathway is initiated when Fas-L binds to Fas receptors on the surface of the targeted cell.
T-lymphocytes. Do you know what a T-lymphocyte is? It's part of your immune system. T-lymphocytes wander around your body and they tag things and they tell the rest of the immune system that it needs to break something down. That's what a T-lymphocyte's job is. Okay, so what happens? What happens if your T-lymphocytes get infected? That's what the AIDS virus does. It replaces the DNA of the T-lymphocyte with its own DNA, making it non-functional. So one of the things that we do when we're looking at somebody with AIDS, we try to determine how many T cells they have. The fewer T cells they have, the worse their immune system is. And of course, that's usually what people die from. They don't die from the AIDS virus. What they die from is a secondary infection that they can't fight off because their immune system doesn't work anymore. And that's what the T lymphocyte does. So this is telling, this is the T lymphocyte wandering around the body, and it is telling a cell that it needs to kill itself. And that's what's going on right now. This is the T lymphocyte up here, and this is the cell that needs to die. So the T lymphocyte is now connecting itself to these receptor sites, and it's going to tell the cell to kill itself, as exciting as that may be. So that's a T lymphocyte. And of course, T lymphocyte is what is infected by the AIDS virus. But in this case, this guy doesn't have AIDS. There we go.
This is another chain of intracellular events that will ultimately result in apoptosis. The sequence is mediated by a Fas-associated desmin, or FAD. In the final step of the extrinsic pathway, caspases activate each other in a self-amplifying process called the Caspase Cascade. Apoptosis is then initiated as the
They're talking about a Caspase Cascade. In other words, it releases all of these proteins. And of course, caspases are what will break down the proteins. So the cascade is a huge influx of, or release of these caspases. As you saw, they're the little saw-shaped things that, well, they're not really saw-shaped. It looks like some kind of a horror movie where it releases all these spinning blades that come and chop people into pieces.
Caspases begin the breakdown of cellular materials. The Caspase Cascade acts as a common endpoint for the second appetite pathway, known as the intrinsic pathway. As its name suggests, the intrinsic pathway is initiated by signals from within the cell. This intrinsic pathway is regulated by maintaining a balance between two sets of proteins in the mitochondrial membrane: anti-apoptotic proteins, such as BCL2 and BCLX, and pro-apoptotic proteins, such as FACS and BAC. In a healthy cell, the anti-apoptotic proteins bind to the pro-apoptotic ones, thereby blocking their action. But if the cell is damaged, or if it stops receiving survival signals, BCL2 and BCLX are blocked in turn. FACS and BAC are then free to punch a series of channels in the mitochondria, allowing mitochondrial substances, such as cytochrome C, to leak out into the cytoplasm. The leaked cytochrome C binds to APAP1 proteins to create a compound that then activates the Caspase Cascade. Apoptosis plays a key role in growth, immune surveillance, and neoplastic development. In all of these processes, there can be abnormalities of too much or too little apoptosis. For instance, cancer cells survive and replicate because they are able to block apoptosis. Understanding the functioning of the extrinsic and intrinsic pathways, as well as of the Caspase Cascade, allows us to design targeted therapies based on better regulation of apoptosis.
Okay, one of the things that happens when you have a cancer is that, just like she was saying, it will start growing, and of course the immune system will try to break down all these cells. So as long as the immune system is attacking the cancer can't grow. And that's how it controls cancerous growth in our cells all the time. So that's part of the process of, that's a part of the immune system process, is it breaking down all of these cells. So there are, and a lot of times what will happen is cancer will start growing, and it's one of your, of course it's one of your cells. It's not something from outside, it's something from inside. So the immune system is wandering around tagging all of these cancerous growths. At your age, probably you don't have nearly as many cancers as somebody my age. I'm pretty old. I'm 68. I'll be 68 in a couple of weeks. So my immune system isn't as efficient as it used to be. Also, the cell division isn't as efficient as it used to be. So as you get older, you start producing more and more of these cancers. And if your immune system is broken down or isn't working very well, then one of the things that will happen is you'll develop a cancer. And you can develop a cancer at any age, certainly. We have infants with cancer. But as you get older, the probability becomes greater and greater and greater. And it's mainly because your immune system is less efficient than it was before, and it's also because you have more cancers forming in your body. We talk about free radicals. A lot of times that's what will happen with free radicals. So the more free radicals you take in, the more fried foods that you eat, the more likely you're going to develop these cancers. Potatoes with bruises in them, those are free radicals, and of course we need to tie those up. You need to cut those out of your food. You need to eat foods that will support your immune system rather than foods that don't support your immune system. So as you get older, of course, you are more likely to develop these cancers. Come on. Okay. The caspases are proteases or enzymes that dissolve protein. The caspases break down the protein and the DNA of the neuron. Normally, Diablo is inhibited by BCL2, and that's what she was saying. Cells that are able to make proper and adequate synaptic connections are the ones that live, while those that don't will die. They will be tagged by the T-lymphocyte, and the T-lymphocyte will tell them to self-destruct. Chemicals that enable proper growth are called neurotropic factors, and that is what we're hoping for. We're hoping for as much growth as possible, as much positive growth as possible. And this is just a joke about, of course, the problem with some of these cells is that they're obsolete, and since they're obsolete, they are told to self-destruct. Well, here's a guy that found out that he was obsolete, so his brain exploded, his head exploded. That's a joke. It's only a joke for scientists that understand what apoptosis is all about. Anyway, his head exploded. Scientists have discovered a substance that promotes the growth of spinal ganglia, and they call this nerve growth factor. A lot of spinal injuries, people that fall on their heads, one of the things that will happen is the skull will cut into the spinal column, and it will destroy that portion of the spinal column. It will sever that portion of the spinal column. Well, we have this nerve growth factor that if we could implant that in that area, we could regrow the cells. But of course, it has to do with stem cells. It has to do with using stem cells. And of course, it's against the law in the United States to do stem cell research. If a technique could be developed to use NGF effectively, spinal injuries, of course, could be repaired back to normal function. Once upon a time, Superman was riding a horse, and Christopher Reeve was his name. He was riding a horse, and the horse stopped very rapidly, and he fell over off front of the horse, landed on his head, and severed his spine. So he was a quadriplegic. He lived for a number of years, hoping for a miracle so that he could he could move again, and of course it never happened, and eventually he died of respiratory failure because, of course, he was paralyzed from the neck down. He had severed his entire spine. I know. So Superman died of having a severed spine, unfortunately. Or the guy that played Superman died of having a severed spine. And of course he was pushing for research with all the IEDs in Afghanistan and Iraq. A lot of brain injuries, a lot of spinal injuries. So we have been pushing this lately, but of course, because of the ban on spinal stem cell research, there's not a lot that we can do. There's more being done in other countries, especially Europe and Canada and Australia, but not the United States. With time and experience, some synapses disengage and other synapses are formed. This process is especially prevalent during cell death in the area, refining remaining synapses to provide optimum connections. And of course, that's what we're hoping for. While neurons and glial cells develop from the same source cells, scientists don't know what informs the cells to end up as one or the other. While neuronal growth takes place almost exclusively before birth, glial cells have their greatest growth surge right after birth, and they will continue to grow throughout your life. So you're making connections, you're constantly making connections. As long as you keep your brain active, you will make these new connections. Synaptic Genesis will be taking place. The glial cells provide myelin for the axons of the neuron. The myelin protects, feeds, and accelerates the electrical responses on the neuron. Myelination allows people to walk with coordination and the brain to process information rapidly. Multiple sclerosis is an autoimmune disease that affects select individuals. The condition allows the immune system, the person's own immune system, to attack the myelin of the neurons and leave gaps in the structure that slows neuronal responses. A couple of years ago, an actress named Annette Funicello died of multiple sclerosis. Every time I talk about multiple sclerosis, I'm trying to think of this guy's name, and I can't think of it. He's a black actor, and he has multiple sclerosis. And for the longest time we were seeing him on television. Now all of a sudden we're not, and it's because the breakdown of his myelin is getting worse and worse and worse, and he can't move anymore. What is his name? I can't think of it. Anyway, some people have multiple sclerosis, and it's an autoimmune disease. It's a disease where the immune system attacks the nervous system. Intrinsic factors in the development of the nervous system deal with genetic factors that allow for proper development. When genetic aberrations occur, it can cause abnormal brain development. Two examples would be Tay-Sachs Disease, which causes the destruction of neurons and eventually results in death. It has been identified as a flaw on the 15th chromosome. Tay-Sachs disease is a fascinating disease. It's genetic. It's genetically passed from one individual to the other. One of the things we know about about Tay-Sachs disease, it is only in a select population. You guys don't have to worry about this because you're natives from the Americas. However, I'm a European. I don't have to worry about it either because my family isn't Jewish. Tay-Sachs disease is a disease of a select group of Jewish people. They're called Ashkenazi Jews. They're the Eastern European Jewish population. So if you know anything about the Jewish population, they had their diaspora. There were 7 tribes of Israel. One of the tribes of Israel ended up in Eastern Europe. So they were in Romania, Hungary, Slovenia, Slovakia, Russia, in that area. And those became the Ashkenazi Jews. The German Jews that were there were the Ashkenazi Jews. The other major group of Jewish people are the Sephardic Jews. The Sephardic Jews ended up in Spain. And of course, they were kicked out by Queen Isabella. And she stole all their stuff. She kicked them out without, and she took all their money. Nice lady. And then she took the money and she gave it to Columbus. And of course, Columbus, in 1492, Columbus sailed the ocean blue, and then he came over here. And after that, there was the invasion of the Americas. Anyway, that's Tay-Sachs disease. It's a Jewish disease. The individual rarely lives beyond the age of 1.5, 18 months. Usually they die before the first year. The nervous system completely breaks down. Down syndrome causes intellectual disability and body abnormalities. It has been identified as an extra chromosome on the 21st pair. But normally everything is perfect. As I said before, the chromosomes all match up perfectly. Almost all babies are perfect. A baby that isn't perfect will probably not make it to the end of gestation, and that's usually what happens. So if there is a problem, then the baby will probably be spontaneously aborted, because the human form cannot afford to raise a child that's not perfect. So usually this doesn't happen. The vast majority of children are perfect. Extrinsic factors include malnutrition, fetal alcohol syndrome, hypoxia-induced intellectual disability. Malnutrition, of course, has to do with not getting enough food. Fetal alcohol syndrome has to do with the mother drinking too much alcohol during pregnancy. And hypoxia has to do with the fact that the child wasn't getting any oxygen when it was being born. It's kind of a miracle the way birth takes place. It takes place it takes about, well, it all depends on the individual and whether she's had a child or not. But sometimes it will take an hour, hour and a half for the baby to pass through the birth canal to be born. If the baby is getting its oxygen through the umbilical cord, if the umbilical cord is impinged, if circulation is cut off, then they have to get the baby out as quickly as they possibly can, because the brain cells start being destroyed after about 3 minutes. So that's not what you want, of course. So if there is any impingement on on the umbilical cord, they need to get the baby out right away. And normally what they'll do is they'll take them to surgery and they'll do a cesarean section. But if they don't realize what's going on, if the umbilical cord is wrapped around the baby's neck, then a lot of times hypoxia will take place. And because of that, of course, we have the death of brain cells, and the intellectual disability will occur. The sum of the intrinsic factors are referred to as the genotype. The genotype plus the extrinsic factors represent an individual's phenotype. When mutations take place in a species' genetic history, the mutation most often creates a maladaptive circumstance. So most mutations are negative, and because of that, they usually die out. But on the rare occasion when the mutation is actually useful to the species, the mutation will be produced and reproduced in the offspring. About 10,000 years ago, the first person with blue eyes was born. Blue eyes, brown eyes, what difference does it make what color your eyes are? Not a whole lot. Brown-eyed people can see a little bit better than blue-eyed people. Blue-eyed people allow too much light to come into their eyes. So for that reason, but it doesn't, it's not life-threatening. So for that reason, it doesn't really make a difference whether somebody has blue eyes or brown eyes. That mutation has been reproduced. Of course, we also have, we have green eyes, we have gray eyes, we have hazel eyes, we have eyes that are yellow almost, brown, not dark brown, but a lighter color of brown that looks almost yellow. Is this something negative? However, there is a mutation that is negative, albinism. Albinism is where they don't have enough pigmentation in their skin or in any part of their body. So their hair is white, their eyes are pink, their irises are pink, and for that reason they don't see very well. And of course that is a negative mutation. So albinism isn't something that is usually repeated. Blue eyes, of course, green eyes, gray eyes, nobody, you know, it doesn't really, it's not a negative thing. You may find blue-eyed people very ugly, that's, but usually people don't really care what color eyes somebody has. Usually they don't anyway. So if the mutation is negative, it will be reproduced. People will be attracted to a select something, and of course it will be reproduced. Albinism is one of those things that people are normally not attracted to. A lot of times they die young because their immune system is, there's a problem with their immune system. You don't see a whole lot of people suffering from albinism. But blue eyes, nobody cares. Experience is an important factor in brain development, of course. The human brain is only 1/4 its adult size at birth, yet few new neurons are added. The reason for the exceptional growth is due to dendrite growth and myelination. Dendrite growth and myelination are induced by experience with the various muscles and sensory organs of the body. So as I said before, as long as you keep experiencing new things, experiencing something, then you can, potentially your brain can continue to grow throughout your life, as exciting as that is. My mother did crossword puzzles, and she did crossword puzzles every day. She got to the point that the letters that she wouldn't put a cross on her A's. She'd make a capital A, but she wouldn't. So it was a TP instead of an A, I don't know. Anyway, but she did this until just weeks before she died, and we knew that she was about to die because she stopped doing crossword puzzle, as confusing as that is. But we knew that there was something going on. Yeah, normally she did crossword puzzles every day. She knew all the answers. She was the most amazing person. So you could ask her what a serf in Anglo-Saxon, in ancient England, when they were Anglo-Saxons, what they were called. She knew all those answers. I mean, the bizarre trivia that they put in crossword puzzles. She hated it when they started talking about hobbits and ints and whatnot. The tree that can walk, that's an int. She hated that because she had never read Tolkien's work. She didn't like that. She didn't like Harry Potter because it was something new. She hadn't read Harry Potter. Anyway. Amblyopia. One form of extrinsic stimulation causing a problem is amblyopia, also called walleye or lazy eye. Children with this problem have a misalignment of the balance of their binocular vision. If left untreated by the age of 7 or 8, the suppressed eye will totally blind. And this is a problem. This is why we have to correct it. And the way we correct it is by putting a patch over the weak eye, over the strong eye, so forcing the weak eye to get stronger. That's what we do. My wife was born with walleye, and because she had walleye, she'd have to wear glasses that had a patch over them so that she could strengthen her eye. Of course, she's fine now. If you look at her eyes, she doesn't have one eye that points off in a strange direction. And this is known as amblyopia, of course. I had a niece that she was is that right? Yes, she was my second niece. She was the niece of my niece. What does that make her? She's still my niece, isn't she? First cousin? I don't know. What? No, I have no idea. Anyway, this child, she was the child of my niece. This individual, they used to keep her quiet by laying her down on the couch and giving her a bottle and letting her watch television. When she was laying down, she always laid down on her right side, watching television with her left eye. So her right eye was covered up. I mean, it was everything backwards here. They strengthened the eye by putting a patch over the strong eye. And what they did, they created a walleye in this child because she was constantly laying down on her right side. The funny thing is, she still does that. She still lays down on her right side. And she will watch television with her left, just her left eye. Or she will close her right eye and she will play with her phone, with her cell phone, as stupid as that sounds. What she has done is they have created a walleye in this child. So she started wearing glasses when she was like 2 years old because this is what they did with her. They laid her down on the couch, fed her a bottle, and she watched television with only one eye. So the left eye became much, much stronger than her right eye. And she's in college today, and of course, she has one weak eye and one strong eye. While treatment in childhood will result in perfect vision, when the problem is corrected in adulthood, the eye does not gain acute vision, and this is a problem. As you can see, he is suffering from amblyopia. This is because when the problem is allowed to remain the same over time, the neural connections in the brain from the weak eye are not as intricate, and of course this lady has amblyopia as well. In her case, of course, since not only is the eye weaker, but the eyelid is weaker as well. So she has one eye that is partially closed, and that is her weak eye. Understanding of amblyopia and other asymmetrically balanced neural connections has been studied by performing binocular deprivation research in laboratory animals. They tortured animals by covering up one of their eyes. And of course they develop normally, except for that eye, except for the weak eye. And the weak eye will lose its vision. And of course we can do this with animals, we can't do this with kids, of course. That would be wrong. But we do it with animals. So we create a creature that doesn't have binocular vision. Dogs, cats, whatever, rats. Nobody cares about rats, but we all care about dogs and cats, I guess. Pigeons, they can do it with just about anything. Researchers have discovered that sensory organs have a sensitive period when the neural development is crucial for stimulation to induce proper dendritic connections. If stimulation does not occur by this time, recovery to a normal state is impossible. And of course, we have done this with language skills. If you don't develop language skills by the time you're 12 years old, then the probability of recovery from the lack of language is terminal. You will never develop strong language skills if you don't develop it by the age of 12. So why in the world don't they teach us foreign languages before the age of 12? Why did they wait until high school to start teaching you Spanish or French or German? And why do you learn Spanish, French, and German even after the age of 12? You're not learning it the same way that you would a language younger. One of the things that we do know is that individuals that learn a language after the age of 12, their vowel pronunciation isn't very good. Just about all languages have their own vowel pronunciations. And because of that, if you could learn it before the age of 12, then you will develop a proper pronunciation of the vowels. Afterwards, it's very difficult to form those letters. So French, which has, their vowel sounds are very much different from English. If I tried to learn French now at the age of 68, I would not be able to make those vowel sounds. I learned Spanish when I was, 14, 15 years old. I still don't pronounce Spanish correctly. I know what the words say. I can pronounce them the way somebody who speaks English would pronounce those vowels, but I do not pronounce them correctly. Anyway, I know it's kind of tragic. Eye dominance. To understand why people tend to have dominant eyes, it must be remembered that each eye represents millions of receptors vying for attention in the brain. When one eye receives more stimulation than the other, some of the synapses in the brain connected to the unstimulated eye become weaker. While most synapses do not fluctuate in their strength with stimulation, some will. These synapses are known as Hebbian synapses. Hebb was the individual that discovered this, that all neurons are not exactly the same. And for that reason, of course, in some instances, if they do not get stimulation, there will be a greater deficit with these cells than with others, with these neurons than others. 50 years ago, the leading cause of intellectual disability in the United States was phenylketonuria, also known as PKU. About 2% of the population carries the recessive gene. Almost all of these individuals that carry the recessive gene are white. So this isn't something that this population really needs to worry about nearly as much unless you have some white ancestry. The gene controls the enzyme that breaks down phenylalanine, an amino acid in protein. Because the enzyme does not break down the phenylalanine, a toxic level collects in your brain and destroys brain cells. So what we have to do is to determine if you have PKU is we have to check your blood as soon as you're born. But we can't check it just after you're born because you have to eat something. You have to consume milk. If you consume milk, of course, it has phenylalanine in it. It has a lot of proteins in it, and you will start accumulating phenylketonuria. Anything that's urea is a waste product, and of course phenylketonuria is a waste product. Phenylalanine is just an enzyme that breaks down protein. It breaks down a specific amino acid in the protein. Okay, so what happens with these children if we don't discover this? What happens is the phenylketonuria builds up in the brain and destroys brain cells, and then they become intellectually disabled. It used to be the leading cause of mental retardation, but now that we are checking all babies, and we check all babies no matter what race they are, despite the fact that it's primarily white babies that have the problem. We check all the babies just to make sure they don't have this. It's a real tragedy. It's something that we could keep from happening does happen. A lot of people don't know their ancestry anyway, not specifically. And that's one of the reasons why they have ancestry DNA, checking everybody's DNA to find out. You've seen that commercial on television where the lady didn't know what she was, and then all of a sudden she found out she's 24% Native American. Now she wants to become a Native American. Yeah, right. That's going to happen. She's going to start dancing at powwows, wearing buckskin. This 70-year-old lady. No. Another lady thought she was Hispanic. It turns out she's American Indian as well. How shocking. I told you my kids thought that they had some Native American ancestry because their mother claimed that she had American Indian ancestry. And the reality was that she's Italian, not American Indian, which gives her a darker complexion, gives her darker hair. And it's funny because my kids don't sunburn. They suntan, but they don't sunburn. I fry, but my kids don't. So we assumed that they had, we didn't know. We had no idea until we did the ancestry DNA. And now we found out that they have more Irish than I do, and they also have more Italian. They have Southern European, and I don't have any Southern European. Anyway, not important. But the phenylalanine is very important. So one of my jobs, I was really good at this, drawing blood from a baby. You don't do it with a needle. You do it with just a punch. So you'll punch a hole in their foot, and then you have to squeeze the blood out of their heel. I know it sounds horrible, it sounds vicious, but the reality is that it can save their lives, right? It can save their brains. It can save their intellectual capacity. So it's something that needs to be done. So you need somebody that actually knows how to do it. Well, I used to milk cows. And milking the blood out of a heel is like a backwards milking a cow. You know, with a cow you squeeze so that your little finger is squeezing the milk out of the teat. But with the heel you do it the opposite way. So instead of going like this, you're going like this. I can't even do it. Trying to convince, and I'll tell you what, there were some butchers out there, and these guys had a really hard time getting blood out of a baby's heel, and they just punch it all over the place. And you'd want to just, you'd want to drill them a couple times. The nurses would get pissed off, you know. But what can you do? You got to get the blood, and it takes quite a volume of blood, unfortunately. I was really good at it. Okay. Williams syndrome is a relatively rare genetic abnormality that causes neural and facial abnormalities as well as mild intellectual disability. Research indicates that Williams syndrome is caused by an incomplete chromosomal structure on the 7th chromosome. These individuals have normal linguistic ability but difficulty in learning by observing. As odd as that seems, so what in the world does the 7th chromosome have to do with, I mean, they can talk, and they talk very, very well. The other thing is, they're the happiest people in the world. There's something about this structure, this 7th chromosome, that has to do with happiness. So these people are the happiest people in the world. They can learn music by ear, but they can't learn by observing somebody. So if you're showing them what to do, they won't learn it. But they can learn, and music, they have musical talents. It's really kind of amazing. And they are so happy. The odd thing is they all look alike. It gives them a different facial structure. Individuals with Williams syndrome have very characteristic facial features. They have broad foreheads, small eye openings. They have low nasal bridges, nostrils that point forward. They have long areas between the nose and the upper lip. They have full cheeks, large downturned noses, and as you can see, the brain structure isn't the same. This is the portion of the brain that this is the occipital lobe in the back, and as you can see, the occipital lobe isn't as big. Their cerebellum is larger. So movement, they can do movement better. They're not better athletes, but music, as strange as that may seem. So as you can see, the brain structure is a little bit different. All has to do with the 7th chromosome. So look at that kid and see if all these 3 people don't look like his sisters. As odd as that seems. They all have the same facial structure, as confusing as that is. So they all look alike, people with Williams syndrome. There you go. Little boy and 3 little girls. Well, one older lady. As you can see, she can play whatever that thing is. Anyway, which isn't it's like playing a piano on your chest. Really kind of odd. There's buttons on the left that you have to punch, and then there's the keyboard on the right. Accordion. That's what that thing is. Down syndrome is a condition caused by the addition of an extra chromosome among the 21st pair of chromosomes. This abnormality can cause mild to severe intellectual disability and various physical anomalies, such as heart malformations and brittle arteries that lead to a shortened life expectancy. But it doesn't have to. Trisomy 21 is more prevalent in older women, probably because of the age of the ova. Research shows that individuals with trisomy 21 have abnormal formations in their dendritic spines, making it more difficult for these individuals to learn, and that's why they have the problem. My daughter had a baby at 42. It was her only child. She had a baby at 40. She got pregnant at 42, and she had the baby at 43. So both of us, she's a biologist and I'm a psychologist, so both of us were well aware of the danger of having a baby so old. Of course, what we were watching throughout the entire pregnancy, there's a possibility that her uterus couldn't be, she'd never used it before, so there's a possibility it's an older fibroid, it's aged, so there was always a possibility she was going to lose a pregnancy. She didn't lose a pregnancy. My grandson is perfect. He's a perfect child, but it's just all pretty much luck. I mean, you really shouldn't get pregnant at 42. If you're going to have a baby, you probably need to do it before that. What else is about Down syndrome? On the Fort Belknap Reservation, the mayor of Fort Belknap is an individual suffering from Down syndrome. He's approaching 60. And the amazing thing is that he's 60 years old. He does have an intellectual disability to some extent, but he's everybody's favorite person, the happiest guy on the reservation, goes to all the powwows. He doesn't dance, but they always call him out, and people, every time he sees somebody, he hugs them. For some reason, he knew my name, and so every time he saw me, he always yelled. One time I was at a powwow, and he yelled across the floor, and he came running across and gave me a big hug, which was kind of cool. He was just a really sweet guy. Still alive, by the way, and he's approaching 60. So normally they have all kinds of interesting problems, heart malformations, and their arteries are brittle, just like somebody with diabetes. But this individual has survived for an extended length of time, and like I said, he's everybody's favorite person. So, and he likes me, so there must be something okay about it. He probably wouldn't remember me now. I don't remember his first name. He's everybody's favorite. Anyway, we'll pick this up right here next time, talking about Fragile X and whatnot. I'll see you guys next time. Thank you for your attention. I know this isn't a lot of fun, talking about all these problems that people have.